Hello students, welcome back to Math 332 Elementary Linear Algebra. This is the second video on the orthogonal complements, and in this video we are going to look at the proof of the fundamental theorem of linear algebra. It's not a very complicated proof. It utilizes a lot of stuff that we saw in the previous video, so this is kind of cool to see how we can put them together and deliver that particular result. So without further ado, let's get right to it. All right, so let's look at the objective for this video. So at the end of this video, you should you should be able to understand the proof of the fundamental theorem of linear algebra, and you know how to apply them. And you will also see that a lot of ideas that we developed in the previous video will come together and give you a very nice demonstration of how we use those ideas in this particular proof. Okay? All right, let's look at the statement of this theorem. Here you are given a matrix A, size is m by n, right? Then, okay, the orthogonal complements of the row space of A is actually the null space of A. This is given here. The orthogonal complement of the row space of A is the null space of A. And the theorem also says that the orthogonal complement of the column space of A, right? The orthogonal complements of the column space of A is the null space of A transpose. All right, so they are trying to tell you that the row space of A, right, and the null space of A, they are related. Okay, they have a relationship between these two vector spaces, and also there's a relationship between the column space of A and the null space of A transpose. Okay, and what are their relationship? These are their relationship. Now, before we prove them, let me remind you of one of the facts that we learned from the previous video. So suppose you have a vector space W, right, which is a subspace of Rn, right? So this is actually a subspace of Rn. So of course it itself is also a vector space. And if you want to compute the orthogonal complement of that subspace, by definitions, what you need to do is you need to find a vector V, right, that is in Rn, such that this vector V is orthogonal to every vectors that is from the vector space W. So you have to have this true. You have to have this true for all W that is in this vector space W. And this vector space W could have infinitely many elements. So this is actually very difficult to carry out, because how do you able to verify that this vector V, right, is going to be orthogonal to all vectors that is from this vector space, right? So this is actually very difficult to do. Sometimes this is like impossible. However, in a lot of times, our vector space W is not in a general form where you can't really describe how their elements looks like. In a lot of times, your W is actually spanned by some vectors. Let's say it's spanned by W1, right, and W2. Now, in this case, the element in W has a specific form. We know that if your W is in this vector space, so your W here must be C1 of some W1, some C2 of W2. And we know from the previous theorem that in these situations, right, in these situations, to compute W perp, you actually doesn't have to make sure that you find a vector that is orthogonal to every vector that is in W. This is just too much to do, but in these situations where your W is like span of W1 and W2, then to find W perp, you just have to find a vector V that is in Rn such that V dot, okay, W1 equals to 0 and V dot W2 equal to 0. That is to say that in order to find the elements that is orthogonal to every elements that is in this vector space W, it is enough just to verify these two conditions. So it significantly reduce the amount of work that we need to do in order to find W perp. All right, so this is one of the main things that you should remember from the previous video. And why do we look at these special situations where your vector space is spanned by some vectors? Well, because if you have a matrix A, right, if you have a matrix A consists of columns, column 1, column 2, for example, the column space of A, okay, is a vector space, right? this one is actually a span of the column vectors C1 and C2, right? So yeah, don't get yourself confused. This one here is number, right? It's bad notation. Okay, so let's put tilde and tilde, right? This is the column space. It spans up the column vector, right? So how about the null space? The row space. So the row space. Let's say you have row 1, you have second row, right? So the row space of a matrix A is a span, right, of the row vectors, right? So this is the row vector. Let's transpose them so that it become column vectors. It's okay. We can identify it with the column vectors like this, okay? So in this situation, right, your column space is actually this, right? Your row space is actually this. So in order to compute the orthogonal complements of the column space, this is going to be easier now. You just have to find all the vectors that is orthogonal to this vector and orthogonal to this vector. If you want to find the orthogonal complements of the row space, you just have to find a vector that is orthogonal to this and orthogonal to this instead of using this original definitions of the, I mean, we're still using it. It's just that we don't really have to go through and verify that your vectors is actually orthogonal to every single element that is in that vector space. We don't have to do that. We just have to do something easier like this. Okay, so this is one of the main idea that we developed in the previous video, and we are going to use it. All right, let's look at the proof of this theorem. So we wanted to prove this, okay, in this video, and this is going to be left as a homework exercise, okay? Now, we know that if you have two sets A and B, so these are sets and these are sets, in order to show that they are equal, you will have to do two things. That is, you have to show that everything that is in A is in B, so you have to show this, and then you have to show that everything that is in B is also in A, so you will have to show this. All right, so you have to show both inclusions in order to claim that these two sets are the same. All right, so now let's look at these two sets that we have right here. So we have the row space of A perp, and then the null space of A, and we want to show that they are the same, right? So you will have to show two different inclusions. Number one, you have to show this, and number two, you will have to show this. Right, let's do the slightly more difficult one, which is this directions right here. You can see that. This is the directions we are going to try right now, which means that we are going to take an element in the null space of A and show that it is definitely going to be an element in the row space of A perp. All right, so let's see how we do that. Like, take an element X that is coming from the null space of A, and we want to show that this element here is orthogonal to every element in the row space of A. If this element here, right, is orthogonal, right, to every element is coming from the row space of A. So if you have row space of A right here, this one dot this one here is 0, this one dot this one here is 0, this one dot this one here is 0, this one dot this one here is 0. So if you can do that, then you will be able to show that this is in the orthogonal complement in the row space of A. All right, and again, as we mentioned earlier, row space of A is actually pretty nice. Row space of A is a span of the row vectors. Yeah, so the row space of A here, right? So the row space of A here is the spans of the row vectors. So row vectors for a matrix, so you have a matrix A, just like what you have right here, right? So the row space of A is the span of the row vector. And everybody know that these are the row vectors. But I want to do something a little bit different, okay? I want to do something a little bit different. I'm going to identify my row vector as a column vector. So we can do that. It's not going to be a problem. So instead of writing out the first row like this, I'm going to write down my first row as a column vector like that, okay? So I am going to write that my row space of A is actually the span of the row vectors transpose, all right? Second row, okay, transpose, right? All the ways to, in this case, we have M rows, so we have M transpose like that. Okay, that is not going to be a problem. So for example, let me give you an example. So for example, if you have 1, 2, 3, right, 4, 5, 6, 7, 8, 9, right? So these are the row, right? These are the row. The row space is actually spanned by all these vectors. But if you look at the span, okay, if you look at the span of this vectors 1, 2, 3, right, 4, 5, 6, and 7, 8, 9, right, 7, 8, 9. Okay, this is going to be, I mean, it looks different, but it's okay. This is going to be the same as the span of this. The span of this, mathematically, they are not different. Okay, they are not different. So I want to identify my row vectors like this, even though the row vector is supposed to be in the row form, but I want to identify it like this. So how do I take this and turn it into this? Well, I take the transpose, right? So I take the transpose. That's the reason why in the notes you will see that I write row space of A as the span of the vectors that looks like this. Okay, so all right, so just in case you lost track of what's going on, let me say that again. So in these situations right here, this is what we wanted to do, right? And I have my row space of A written as the span of the row vectors, but written in this way, okay? And all the ways to Rm, okay, transpose. So this the row space of A. I take an element that is from the null space of A, and I want to show that this element is orthogonal. Is orthogonal to, right, every element, right, every element, okay, in the row space of A. But because the row space of A is like this, so we don't actually have to do that. Okay, in fact, we just need to show that this is orthogonal, right? This is orthogonal to, right? In order to achieve this, we just need to show that this is orthogonal to these vectors, right? These vectors, and all the ways to these vectors. Okay, so this is already enough. This is already enough to show that this X is going to be in the orthogonal complement on the row space of A. Okay, makes sense? Right? Think about it. That's the definitions and the tools that we learned from the previous video. This is kind of like the definitions, right? This is a definition, right? But then because the row space of A looks like this, so we don't really have to do that. We just need to do this. Okay, let's do that now. Now, if you have an X that's coming from the null space of A, right? So you have X is coming from the null space of A. What does it mean? It means that this A of X will be equal to 0. Okay, that's the definitions of X being in a null space of A, right? So let's look at this particular matrix right here and write down the row vectors. Okay, write down the row vectors and also write down the X vectors, right? So we write like this, okay, and pretend that we multiply. So we are multiply. How do you multiply a matrix? We take this, multiply this, and you get this, right? Okay, and then you take the second row, right? Multiply this, you get the second entry. This is how we usually multiply matrix, right? And then finally you have this, multiply this, you get this. So what happened is you are taking a row vectors, right? And then multiply, this is multiplications. So let's look at our previous, so for example, let's say the first row is 1, 2, 3. Okay, and let's say your X here is X1, X2, X3, for example, okay, for example. So when you multiply a matrix, this is multipliable, right? So this is 1 by 3. This is 3 by 1, and you're supposed to get a number, right? So that number, what is that number? That number is going to be 1x1 plus 2x2 plus 3x3. And instead of multiplying like this, this is the same as if you are taking this 1, 2, 3 and dot, okay, your x1, x2, x3. You get the same result. You see this? The matrix multiplication and the dot products. It's the same thing. So just now, when I was doing this circling, right? So just now, when I was doing this multiply this equal to this, well, instead of writing it like that, I can also write it as a dot product, but transposing my row vectors so that this is an element that is 3 by 1, right? This is 3 by 1. It has to be the same column vectors like that in order to talk about the dot products, right? So dot products is defined like this, right? And this is the matrix multiplications, right? And this is the matrix multiplications. All right, so the key observation is that if X is in the null space of A, then you have this and you have this. That means that, look, your X is orthogonal to the first row, okay? Your X is orthogonal to the second row. Your X is orthogonal to the M row. So because your row space is identified like that, that means that your X now is actually orthogonal to every row. And because your row space is defined as a span of that, this is already enough. This is already enough to demonstrate that the X that is coming from the null space of A is actually also a member in the RA perp. That's how you show them. And since this X is any arbitrary elements that's from the null space of A, so you establish these inclusions. So we establish these inclusions. Does that make sense? So we don't really have to show that it is orthogonal to every row vectors, every elements coming from the row space. We just need to do this, and this is enough because of this. This is how we utilize the theorems that we saw in the previous video. So that theorem is how we establish this. Okay, so we have this result. All right. Now let's see what happened in the other inclusion. Okay. All right. For the other inclusions, we have null space of A, and we want to show that everything that is in the RA perp is in the null space of A. So we want to show these inclusions. So what do? Again, we take an element that is from here and show that it has to be in here. All right. Does that make sense? Let's say it one more time. We take an element that is in here and show that it has to be in here. All right, let's do that. So we take an element, X, that is coming from the row space of A perp. Okay. All right, so X is an element that is orthogonal to every single element that is from the row space of A. So you have X. This X is orthogonal to this vector here. This is orthogonal to this vector here. That's orthogonal to this vector here. That's orthogonal to this vector here. Right? This is orthogonal to every element that is coming from the row space of A. Now, let me ask you a quick question. What is the things that is in the row space of A? Remember, our matrix A is have first row like this all the ways to the M rows, right? And the row space of A is the span of all these row vectors. So we know for sure that the first row like that is in here. The second row is also in here all the ways to the M row. I mean, the row space of A contains a lot more than that, but we know that this one right here is definitely in the row space of A. This row is also definitely in the row space of A, and this row is definitely in the row space of A. And since X has to be orthogonal to all these row vectors, that means what? That means that the X here dot, let's say R1, okay, transpose, have to be equal to 0, so on and so forth. Right? So this is the key to understand what is in this box right here. All right, so let's look at them. Now, let's take an X that is in the row space of A perp. That means that X dot Ri transpose is equal to 0 for all the I. That means if you put this result in this form, right? You put this result in this form, just like what we did just now, right? So this one equal to 0 can be represented by X dot R1, okay, transpose equal to 0. It's the same thing. So this result give you this. Okay, second one give you this. Third one give you this. That means that if you write everything out, you write all this thing out in the matrix form, it will give you the 0 vectors. All right, so let me say that one more time. If you write all this thing out one by one in the matrix form, you will get this. Okay, the reasoning is exactly like the one that we have before. Right, so if you look at this one right here, it's exactly the same reason like this. Okay, exactly the same reason like this, and we are using this. We have used this before. Now we are just going to do it one more time, right? So in the other direction. So this one here give you this equal to 0, give you this equal to 0, so on and so forth. That means X being in the row space of A perps will give you this AX equals to 0. That means that this X that is originally from the row space of A perp now will make AX equal to 0. So this X here that is from here will make AX equal to 0. So by definition, this X is actually an element in the null space of A. All right, and since this element that is from the row space of A perp is any element and any elements that is in here is in here. So we have established this inclusion, and together with the previous inclusions, we will have the result that we need. All right, so we'll have the result that we need. That's it. It's not very complicated. And so it's not very complicated. So let me write down what we have proof. So we have proof that the row space of A perp is the same as the null space of A. And actually, there's a theorem that we're going to prove very later in the next video, that if you have a vector space, so we haven't proved this yet, this is a result that we can use. So if this is a vector subspace of Rn, if this is a vector subspace of Rn, we also demonstrated that the perp is also a vector subspace. The orthogonal complement, right, of W is also a subspace of Rn. So we can also take that perp again. So we have W perp perp, and W perp perp is going to be W. This is something that we will show in the next video, but let's say we are using this now. If we use this now, we can also see that if you perp this again on both sides, we will have the row space of A is the null space of A perp. Right? That's just to say that they are orthogonal complement of each other. The row space of A and the null space of A, they are orthogonal complement to each other. All right? So that's what it said. And this is the remark that we have right here. Okay, so now let's look at how we apply them. So I have questions for you right here. So the question is, all right, so find a basis for the orthogonal complement in R4 of the subspace given by the, so you have W, right? So this is W, this is W, right? So this is a span of these two vectors right here. Right, these two vectors right here. The question is, how do you find W perp? We can do it in many different ways. In fact, I'm going to show you that how this is done in multiple different ways. But think about it. Use whatever you want. Use whatever you want. I want you to find a basis for the orthogonal complements of the space. All right. So basically, I just want you to find, what is this? This is a vector space, isn't it? And if this is a vector space, you should be able to give me a basis of this vector space, something that span this space and also being linearly independent. All right, so let's do that. All right, I will give you a couple of minutes to work on the problem, and you can pause the video, and when you are ready, you can restart the video, and I will come back and we can look at the solution together. All right, let's look at the solution. So W is spanned by, let's call this vector W1, and let's call this vector W2. So using the theorem, we can say that, hey, if you want to find W perp, then we just need to find all the vectors, right? All the vectors that is in R4 with the property that the X dot, the first W1 will give you 0. And X dot, the second, okay, that's the W2 will give you 0. So you basically just try to find all the vectors that's orthogonal to this vector and this vectors, and that is enough to identify all the elements that is in W perp. We can use this theorem. So let's write it down. Right, this first dot product gives you this equation, and this second dot product gives you this equation. So what do we want to do? What we want to find? We want to find all the component x1, x2, x3, x4. Right, because this will give you the vector x. All right, so let's do that. Put this system into the augmented matrix, row reduces it, and you can see that we have all this free variable. We can write down our solutions, and our solution looks like this. So we know that every element in W perp is spanned by these two vectors, and you can also verify that these two vectors are linearly independent. So these two vectors can be chosen to form a basis for W perp. So this is not applying the fundamental theorem of linear algebra at all. We are just using this theorem right here. If you still remember, we are using this theorem right here. If you look at the book, your notes, you are basically just like, I don't care, I understand this theorem, so let's just use this theorem, right? W, if it's a span of all these vectors, a vector V that is in is orthogonal complement if and only if the dot product with all the W that is inside the span is 0. That's one way to do it. That is one way to do it, okay? And we can also use the fundamental theorem of linear algebra, and we'll be like, hey, so we have 1, 2, 2, 1. Let's take a look one more time. So we take this 1, 2, 2, 1, and 3, 4, 2, 3. Let's put it as the row of the matrix. So 1, 2, 2, 1, put it as a row of the matrix. 3, 4, 2, 3, let's put it as a row of this matrix. So the W, which is the span, right, the W, which is the span of our W1 and W2, look at this span, all the possible linear combinations of this, all the possible linear combination of this. This, if you put it like that, okay, this is actually the row space of A. All right, this might be a little bit tricky. You'll be like, wait. Their orientations are different. One is a column vector, one is a row vectors. How can you claim something like this? Look at it. Look at it. If you write it down, what does this thing mean? This is all the C1, okay? Okay, let's use K just in case I need C somewhere else. This is 1, 2, 2, 1, all right, plus K2, right? 3, 4, 2, 3. We're looking for all the vectors that looks like this. If you write out matrix A like this and you look at the row space of A, what is the row space of A? Row space of A is the span of the row vectors, okay? 1, 2, 2, 1, all right? Okay, and then comma 3, 4, 2, 3, right? So if you look at this 2, okay, you look at this 2, and you look at the elements inside this, so these are going to be some kind of S1, right? Multiply 1, 2, 2, 1 plus S2 multiply 3, 4, 2, 3. So this 2 is the same in a sense. It's just one standing up, one laying down, but they give you the same result. It's the same span. It's the same span, right? How do you multiply this? You have K1 of this, K2 of this. I have S1 of this, S2 of this, so on and so forth. They are the same thing. You take a look, you look at it closely, they are the same thing. So I can identify this span, right, which is the questions given originally. I can identify this as the row space of A if my matrix A is given like this. So this is what we call the key steps. The key realizations is that I can identify these two spaces to be the same. I can identify these two spaces to be the same, okay? Now with this, the fundamental theorem of linear algebra says that, okay, if you want to find W perp, that is the same as you try to find the row space of A perp, and we know that the fundamental theorem of linear algebra says that this is the same as the null space of A. All right, so this is the same as the null space of A, so we just have to look at this matrix A and find the null space of A. What does it mean? Well, it means solve the system, AX equal to 0. Solve the system, AX equal to 0. And this is something that you know how to do. I'm not going to do it again. In fact, actually, it is right here, actually. You see it? It's the same thing, right? It's the same thing. You get the same answers. Exactly the same computation from before. Nothing really different, right? You can see it's finding the null space of A is the same computation that you have it here. That means this is again the basis. All right. Okay. So there's another method. That's the last one. That's another method. So this one here, okay, again, your W, right, is the span of these vectors 1, 2, 2, 1, and 3, 4, 2, 3. All right. So if you're having trouble placing it laying down, you can also place it like that. This is our matrix A, so W is the column space of A, right? Because the column space of A is a linear combination of the column vectors, which is exactly the same as this. So you can also write it like that, right? So your W is the column space of A. Now, we want to find W perp, isn't it? So that means that we have to find this perp, and this is the same as the null space of A transpose. What does it mean? You take this A, you transpose it, 1, 2, 2, 1, 3, 4, 2, 3, right? This is your A transpose, and you try to solve, okay, you try to find an X so that is equals to 0, right? So you try to solve for this X. And this computations, ladies and gentlemen, is the same as these computations. All of them leads back to the same computations. And again, you will get the same result. You will get the same result. Everything is the same. So no matter what you do, either you use the definitions, all right? I mean, not really the definition, the theorem, all right? The theorems, this theorem, oh man, we have to go up again on page 3. this theorem. Either you use this theorem or use the fundamental theorem of linear algebra. It doesn't really matter. You use the row space or use the column space. We all get the same result. That is, in this case, we can choose this as a basis for W perp. All right, so we can choose this as a basis for W perp. Okay, that's the end of our presentations for orthogonal complements. And the next thing we were going to talk about is orthogonal projections. All right, so we're going to talk about orthogonal projections in the next video. Again, all these are important topics that is we're going to put them all together at the very end of the semester when we talk about the so-called least square methods. All right, see you in the next video.